Swayam Prabha. Digital India. Educated India.
Welcome everyone to our online NPTEL course Environmental Chemistry and Microbiology. I am Professor Anjali Pal from Civil Engineering Department. I am covering the environmental chemistry part. This is my lecture, fourth lecture on acids, bases and salts. Today in my lecture I will tell you about the indicators. You all know that indicators are very important in titrations, and we know that there are many different kinds of indicators depending on the what type of titration I am doing. We have to choose the indicator. So, for example, there are acid base indicators which we use for acid base titrations. There are some metal ion indicator which we will use for metal ion determination, say for example, for hardness determination. There are some redox indicator which we use for redox titrations, and there are some adsorption indicators also which we use for other purposes. Now, because we are talking about the acids, bases and salts, now I will tell you about the acid base indicators. We all know about the two indicators. One is the phenolphthalein indicator and another is the methyl orange indicator. We all use, even from our school days, we are habituated in using these two indicators for our acid base titrations. How it is happening? Why they are changing the color in during our titration? When it is acidic, it shows one color. When it is basic, the solution is basic, it is giving another color, that I will tell you today. Now, I am starting with the indicator phenolphthalein. Before knowing this phenolphthalein, we must see the structure, and we must know the what is tautomer. Okay, tautomer. We know isomer. Isomer means two different molecules or maybe one molecule. If they have different structures, then they are isomers. Now, here it is also tautomers means a special type of isomer, but indicators are weak organic acids. We have already seen that organic acids, acetic acids, formic acids, and they are weak. That also we now know that carboxylic acid group, that is the organic acid, is weak acid, and the phenolphthalein, I will tell you that tautomers, what is the characteristic of the tautomers. Okay. Tautomers, they can exist in equilibrium. They are the different forms of the same molecule, and one form is non-ionized form, another is the this non-ionized form is showing one color, and the other is the form which is capable of ionization, that is giving another color. Now, if we represent the non-ionized form as HIN and the ionizable form as HIN1, then we can tell that it is the equilibrium between HIN and HIN1, and HIN1 immediately dissociates because it is ionizable form. So, it can dissociate into H plus ion and IN1 minus ion. These are all the characteristics, and I am talking about phenolphthalein now. The non-ionized form HIN differs in color from HIN1. Okay. So, the color of this one and this one is different, and obviously this color and this color, this is the color which is the color of the ionized form. Okay. And the indicator ion, so the color of HIN is different from that of the IN1 minus. Okay. Now, here comes the structure of phenolphthalein. Okay. This is the structure of phenolphthalein. So, tautomer, before going to this I must tell you what is tautomer. Okay. Tautomer, I have told you that this is the isomer. Okay. So, here you can see those who are from chemistry, they already know what is this. This is nothing but acetyl acetone. Okay. And it has two ketone groups, the CO means C double bond O here, C double bond O here, and these two carbonyl group is separated by one CH2 group, and here you can see that C double bond O has become COH, and here the double bond is formed here. Between this carbon and this carbon there is one double bond. That is why it is called enol. Enol means in and all. In means double bond, okay, and all means alcohol. Okay. So, in this form there are both this group, that is the double bond, and also the OH group, that is why it is called enol, and this is the keto. So, it is the tautomer, this form is the tautomer of this, okay, and this is called keto enol tautomerism, keto enol tautomer, a keto form and enol form, whatever may be you can call. Here also, so what is happening here, if we look carefully, then we will see that one hydrogen from here is coming here to this oxygen, and that is why the double bond is formed. So, here you can see that instead of CH2 it has become CH, and this instead of O it has become OH. So, basically this hydrogen from here it is coming to this oxygen, and this is the characteristic of the tautomerism. Okay. So, one atom or one group can change its place, okay, giving two different forms, okay, and this is in equilibrium. So, here also it happens same way. If you look into this structure, you see it is the OH. So, hydrogen is present here, but now this hydrogen is coming, this bond is broken and this hydrogen has come here. Okay. So, this form and this form are the tautomer, okay, just like this one. Here it is the structure, the compound is different, that is why it looks different, but basically this is also tautomerism. Okay. Now, about the color, this one you see chromophoric group means there are some double bond, single bond, double bond, single, the alternate double bond, single bond, if it is there, we know the color is developed. Okay. So, here this type of bond is not there, that is why here this is colorless form. Okay. So, phenolphthalein, when it is present in this form, we see no color, that means it is colorless. Now, if you increase the pH, that means under alkaline condition, you know that this form is generated, first this form and then it comes here, because hydrogen is taken away by the alkali. So, this form is generated and this has pink color. So, we have used phenolphthalein. If you remember that when we say, for example, I take some acid, okay, acid solution, okay, say for example, HCl solution, okay, and we put a few drops of phenolphthalein. So, what will be the color? It will be colorless, we see no color, because HCl has no color. Phenolphthalein also in acidic condition it does not give any color. Okay. Now, if I start adding some NaOH solution there slowly, and when the neutralization point will come, that means the pH will be around 7 or maybe more than that, then we will see that the color now has become pink. Okay. Why it is pink? Because phenolphthalein has changed its structure. Okay. So, this is the mechanism. So, in acid solution it will have this structure, and when you add alkali slowly it will be converted into this structure, same compound, but two different structures, and they are nothing but tautomers. So, here it is colorless in acidic condition, here it is pink in the alkaline condition. This is the, so this is an indicator, acid base indicator, and in presence of acids the equilibrium is shifted to the left and the indicator consists mainly of the non ionized form, colorless form, and in presence of alkali the equilibrium is shifted to the right and the solution gives the color of the indicator ion, that is pink color. Now, there is something going on, it is very similar to the equilibrium of the acetic acid that prevails in water medium. It is, you will find the similarity. Okay. The color therefore depends on the H plus ion and the of the solution by the relation. How? K indicator, this is the equilibrium constant because it is, you can think that the H in is giving to H plus plus in 1 minus. Okay. I have shown you the equation in the previous slide. So, if you consider that equation, then K you think about this equilibrium constant. So, K indicator, that is why in is written, K is equals to nothing but H plus ion concentration into in 1 minus that concentration by H in, that undissociated form, that is the concentration. Okay. Now, if you change the place then and then you take the log minus log, then you will get that pH is equals to pK indicator plus log ionized form by non ionized form. It is, you will find the similarity with the acetic acid, that buffer also, na, the buffer solution, where K indicator is the ionization constant of the indicator, also called indicator constant, and pK indicator is nothing but minus log of K indicator. Okay. Now, comes the acid base indicators. When we will see colorless and when we will see the colored form, because it is the mixture of two forms. So, one color will be predominating when, okay, because it is titration. So, you have to know that neutralization point, right. So, this is very important to know that the color is visible when one form is about 90% and the other form is about 10%. It may be 95% and 5% also, but at least 90% it should be, unless, because say for example, both the forms are present 50-50, then you will not visualize the color. Okay. One form should be in excess, how much excess? 90%, another form is very low concentration, that is the 10%. It is evident therefore, an indicator changes its color over a short but definite range of pH, pK indicator plus minus 1. Okay. That log 10 is to 1, not 10, actually 9 is to 1, right, 9 is to 1, that is why approximately plus minus 1 I have written. Okay. That means the choice of indicator means for any type of titration, it is very important to choose the indicator. There are so many different kinds of indicator. Okay. You are the person to choose the indicator for a particular titration. Say for example, pH, each indicator, there are so many indicators, methyl orange, methyl red, bromocresol green, phenolphthalein, litmus, thymine, these are very common. Other than this, there are many other indicators. Okay. And each indicator has its characteristic pH range where it changes its color, and that is coming from here only. So, 3.1 minus 4.8, 3.1 not minus, 3.1 to 4.8, this is the range. For methyl orange, it is the range. For methyl red, 4.2 to 6.3. Okay. So, there are different ranges where it changes the color. For phenolphthalein, 8.3 to 10. Okay. Now, what is the characteristic, means which there are, if you have more choice, then which indicator you will choose, what characteristic should be there for a good indicator? A sharp contrast of color in acid and alkali solution. I like phenolphthalein very much. Why? Because you see the contrast, means in acid it is colorless, okay. In alkali it is pink. So, you will see the color change, very drastic color change, okay, in the neutralization point. But for methyl orange, you know that methyl orange in alkali it is yellow, and in acid it is pinkish red. So, methyl orange if you use for acid base titration, you have to be very careful, it needs some trial also, you need some experience also to use this indicator, because the change from yellow to pinkish red or pinkish red to yellow, you know the change is not like phenolphthalein, it is not sharp change. You will see slowly it is changing the color, and you have to be very careful that okay, this is the end part. Sometimes you will be confused also. Okay. That is why it is told that contrast of color, a short but definite pH range for a color change, and a rapid tautometric change of the indicator on change of pH. Means one form to another form, it should be very fast. Otherwise, if it takes time, the equilibrium the should reach very fast. So, that is also another thing for the indicator, and that characteristic for the indicator. Now, choice of indicator, how you will choose a indicator? Okay? There are different kinds of titration you may take up. So, for example, for acid base titration, there are maybe 4 different types. So, for example, it may be a strong acid versus strong base, it may be strong acid versus weak base, it may be weak acid versus strong base, it may be weak acid versus weak base. Okay. So, examples are also written. Strong acid, strong base, it may be HCl versus NaOH. Strong acid versus weak base, maybe HCl versus ammonium hydroxide. Weak acid versus strong base, maybe acetic acid versus NaOH. Okay. Weak acid versus weak base, it may be acetic acid versus ammonium hydroxide. So, there are so many different kinds. Okay. Then how will you choose which indicator you will choose for these titrations? So, with an example it is shown. Okay. It is an indicator, it is a titration between the strong acid HCl. You have taken 50 milliliter of n by 10 HCl for example, and in a conical flask. Okay. And then you have taken in the burette, you have taken NaOH solution, n by 10 NaOH solution. Then you have started your titration. Okay. Then say for example, when you have added NaOH 45 milliliter, basically the neutralization point should come when you will add 50 milliliter of NaOH, because you have taken 50 milliliter of HCl and the strength is same. Okay. So, but we have started from thinking about addition of 45 milliliter of NaOH. So, what will happen? What will be the pH? When you add 45 milliliter already added the NaOH solution, then pH will be like this. If you calculate it, then also you can do it easily. Okay. Then say for example, you have added already 49 milliliter of NaOH to this HCl solution, then pH will be like this. Then you have added 49.5 milliliter, then pH will be like this. You have added 49.9 milliliter, pH will be like this. Then 49.95 milliliter, okay, pH will be like this. Then 50 milliliter, so it is neutralized, totally neutralized. So, it will be 7, pH 7, and then you have added some extra drops, okay, then pH will be like this. Then another drop, then it will be like this. Okay. So, we must carefully observe here. It is just before the neutralization point, it is 4.3, and this is just after the neutralization point 50. So, it is a huge jump, okay. Okay, huge jump, where to where? 4.3 to 8.7, okay. Just 2 drops addition, okay. It is changing so much. That means there is a huge jump, okay, huge jump, and this has been shown by this curve 1A 1B. So, this is 1A, this is 1A and this is 1B, okay. Here to here, huge jump. So, in this case where you are titrating a strong acid with a strong base, then you can choose any indicator, all indicator will fall in this range, okay. It is a huge range, right. So, you can choose any indicator, okay. But in case of say this type of titration, strong acid versus weak base. Okay. Then this is the curve 1A versus 2B, 1A and 2B, this is the curve. So, the range is here only, here. Okay. So, you can choose some indicator where the pH range will fall in this range. Okay. But if your titration is like this, weak acid and strong base, say for example, acetic acid and NaOH, then 2A 1B curve, that means this the pH change. Here you can see x axis and y axis. In the x axis here it is 100, but here it is percent neutralized. Okay. This is percent neutralized of acid and here percent neutralized of base, here 100% neutralized. So, in case of this one, weak acid and strong base, 2A 1B. So, 2A and 1B. So, this is the range. Okay. This is the range that you have to think when you select the indicator. But this titration is not very good titration, weak acid and weak base. You can see that there is this is the curve 2A 2B, means it will be like this, it will be like this. So, here the range is very narrow range. So, almost no indicator will fit for this type of titration. Okay. So, for a given titration, the indicator should be selected in such a way that its pH range coincide with the sharp change of pH at the equivalence point. Okay. So, it is your job to choose. There are so many options. Okay. Depending on which titration you are doing, you have to select the proper indicator, otherwise you cannot do the titration. Okay. This is very important. For indicator selection, you have to think a lot. Okay. But obviously, it is the acid base titration, it is not other type of titration. Whatever I have discussed is acid base titration. Now, here one interesting slide I have given to show you the color of phenolphthalein. This is the color of phenolphthalein, you know, this is the NaOH, okay, NaOH solution, and phenolphthalein you have added. So, it is very dark pink color. Depending on the volume of that concentration of phenolphthalein, you may get either very dark color, dark pink color or light pink color. Okay. Here quite a few drops of phenolphthalein have been added, that is why it is dark color. Now, you are adding ammonium chloride, say for example, from outside here. So, what we will see? It is a salt. You may think that okay, so it will remain the same, but ammonium chloride, I have told you that it is a salt of weak base and strong acid, that means ammonium hydroxide and HCl. It is a salt of weak base and strong acid, that means it will behave like an acid. Okay. So, when you are adding, you can see that slowly it is being neutralized. It is being neutralized. Ultimately, you see the color is becoming, phenolphthalein is becoming colorless, that means it is showing the towards neutralization. Okay. And then finally, you will see that finally that final solution I have not shown, but it will be colorless obviously. That is because of the hydrolysis. Okay. Ammonium chloride, when it is hydrolyzed, then it will produce what? Ammonium hydroxide and HCl. HCl is stronger, that is why ultimately it will be neutralizing the solution. Okay. This is a very interesting experiment that you can also do. Okay. Thank you so much.